particular to it. So
this call is now being recorded.
I'll just go to the notification of the recording. So no, we're not changing this. I think you're seeing nothing at the moment. So now I'm going to start sharing, but we will start sharing from the last slides, the last PDF anyway. So in that one, we had finished deriving the Schrodinger equation as well as the time dependent Schrodinger equation. So we had already derived those two. And we said that we mostly use which one? The time independent one. And so just need to do some, if it works or not. So we said we mostly use the time independent Schrodinger equations. So now you're getting confused. The independent one is the one without time. And then the one with time is the dependent one. So occasionally people have been confused once in a while. So the difference between those two. Now we are going to look at some conditions we have in this equation, and these conditions will help us when we're trying to get solutions. Let's see. I don't know what will happen, but probably weird. Okay, let's try that. So you'll soon be seeing something good. To everyone. I think you should be able to see it. If not, it will show up in a few seconds. So look at the solutions of Schrodinger's equation, and we get the time independent by separating those variables of the wave function into what you call the spatial coordinate, which is psi x. And I think we can just look at psi x. And then the time dependent part, which is psi t. So this is what we have here highlighted. We have this is the spatial. Okay, let's see here. That's the spatial coordinate and then the time coordinate. So once we separate these variables, we can differentiate them and then get the time dependent Schrodinger equation. So there are just a few errors corrected there in that bit. So whenever we can get the spatial coordinate, it means that we can just add the time dependence term, so that we go for the total solution. Now, we remember we are looking at this equation as, so if it has Vx, Vx can also be a function of time. So also we are taking time independent potentials. You guys will look at more of what happens with these time dependent potentials in fourth year anyway, when you're looking at antennas. Okay, you first look at them in second year, of course, but retarding potentials and what. So when your signals go out in time, your signals you receive on the phone, wireless signals are voltages, actually, electromagnetic voltages. So once you vary voltage, you vary the amplitude of the signal. That is what you use for your old eye. Okay, now it is no longer there. You have the digital transition, but in the digital signals, they have an analog. You had the old TV, really, it was really a sequence of voltages. We are going to look at conditions of Schrodinger's equation. And then one thing to emphasize is that Schrodinger didn't have this equation, and we have also not been saying we're having a lead up to Schrodinger equation, but sometimes you might be asked to derive it, so you don't write impossible. But we said that one, you have the conservation of energy, and of course, after the conservation of energy, where you have the total energy is equal to K plus KE plus PE, or T plus V, and then you assume one function, which was assumed. So we're going to see how we get this wave function actually, first of all. So we're going to look at eigenvalues and then eigenfunctions. So every time we solve this equation, we're going to see that you end up with a number of solutions, phi1 up to phi n. By now you're used to multiple solutions from your differential equations. I think some people need to mute. I'm hearing some crackling in the background. Let's see. Change is off. Yeah, and welcome Nandi Swabra. It's off. Makwaya Willard is off. Message Francis. Ronella Nambi. Nanjebe John. Kola Ronald Mutegeki. A. Rogers. Mutunji. Nachisa Kennedy. Crazy is there. Kenya John. Namugwaya Mary Patience. Dodwa Faruku. Mary Henry. Emmanuel Otekayot. Yeah, now I can pronounce it after a lot of practice. Popular Tech. I think we'll post his name again. And Ron Udapa Ambrose, Catherine Namboga, Mwezi Bob, but Helena Tukwase, Marija David, Wembabazi Timothy, Adam Beam, Academia Global, might have to post them again. Hagai Youth, Isaac Waligo, Kalemba Ian Kennedy, Mkashaba Godwin, Genoga John Bosco, Millicent Nebe, Mark, no, that's me, Odong Sam, Henry Emmanuel Apolot, Jordana Chantal, Keith Membe, Ndechiani Kapo, Kaizi Abdul Jr. The first and second. Yeah, who is Jimmy Jobs? This is the first time I'm seeing Jimmy Jobs. I think maybe the first class. John Stavy, Amanda Charles, Rebecca Letitia, Kenya Grace. I think it's honestly the same people. I would actually love to know how you guys are whatevering from and joining us from. I know you're mostly at home, but I would like to know which part of the globe you're in. This time we had somebody. Were they joining in from Tanzania? I don't know. Anyway, you're most welcome. So we're going to see a number of conditions that we need. Some of them I'll be referring to the math that you've done, but some of them I'll try and explain them. So let's just get some paint. Don't worry. This print screen is going to paint. So just share the paint version. So that's the paint version. As usual, we'll try and get out the stuff we don't need. We need some bit of the Schrodinger equation. Let's just remove that for now. By the way, he's had a good weekend. I know some people may not be with us because of the games. I think they were happening late, so but I was told by the Man U fans that Arsenal lost, so that is life. Somebody was threatening to arrest people in case they mention him and Arsenal, but that is on a lighter note. But it is, I hope it is for entertainment, but some people take super seriously. So I think we're done with this bit of the cleanup. But I've already looked at the lead up to this, so I don't think we should have it here. We'll concentrate on explaining these conditions now. Now, the wave function is going to be, it is plotable, so it's not some weird. Go on. I thought I may need to get a new mouse pad. So I'm going to increase the size a bit. So there are different types of graphs that you have. So this is going to be, let's assume that this is your function, psi x or psi t, and then that is t. Sometimes given as psi x t on there as well. So now we know that they're going to be, so that is the wave function. Then your potentials can also have interesting shapes. The potentials can also have interesting shapes. So they can have interesting shapes. Of course, energy is a scalar, so integer is a scalar. It will just be a certain value, a certain level somewhere. But having energy in terms of wave, I think is meaningless. So we're going to see what happens to these conditions. Now, these conditions are important, first of all, because if there's, you see, if you derive something, they've put restrictions already to as you're deriving it. Since this was not necessarily derived, we're just actually proving that the Schrodinger equation, okay, there's another proof for that, but that it's consistent with de Broglie, and it's consistent with the conservation of energy, and it's consistent with all these principles that we know to be true, both classically and quantumly. So we're saying that we have these wave functions. We impose some conditions to these wave functions. So, for example, the first one is that the integral of this wave function, you remember, according to Max Born, it represents the total probability of finding the electron anywhere within that. And that it must be finite. So the integral can't be infinite. The integral can't be infinite. So first of all, that this integral is finite. And then second of all, that phi must be continuous. Now we're going to look at, okay, I think let's just cut this stuff out. What does it mean to be continuous? You guys are called continuing students. What does it mean? So continuous means that there are no breaks. There are the number of functions which look like they are continuous, but they are not. Let us say y is equal to 1 over x. Is that a continuous function? Y equal to x. Is that a continuous function? But the continuous is not written with the W. It's like continuous. So let's see. So we're going to first plot y is equal to x. So y is equal to x means for okay, which one is y, which one is x? That's good. That's a good question. So you have y and x. So yes, James Migo. James, many people with these days names are Africa-wide. They are no longer restricted to certain regions. So I think for the first time we're going to use blue. So we want to draw the curve y is equal to 1 over x. So that means that as y tends to 0, x tends to infinity. Then as x tends to 0, y tends to infinity. So we know that as x tends to 0, y tends to infinity. And as x tends to 0, y tends to what? No, as y tends to 0, as you're descending this bit, x tends to infinity, because 1 over infinity is 0. So you have that sort of graph. Now you could argue that this meet at infinity, but we don't think so. So if you look at a portion of, okay, it should ideally be with respect to time. So let's just, but anyway, continuity can either be in coordinate or in times. This is not really one. So let's just say that's delta x. So within this delta x, or within a certain range, or the integral must be continuous. Now it can be piecewise continuous, something like that. So actually this function is, it has a certain value at x is equal to 1 and x is equal to 2. So this function is piecewise continuous. This counterpart is, we can use another color since piecewise continuous, because out of this, as in there's no value where the function is undefined. Undefined means that it's either infinity or there's no value, not necessarily 0. For example, if you had another fourth function, let's say like that, so that function is undefined within this range. And what? Okay, it's undefined. I don't have time to write. So it's undefined within that range. So anyway, back to this, 1 over x, you can see is not continuous as x tends to 0. As x tends to 0, it's not continuous. So you don't want that happening to a function. Then single valued, you can see that at this point, as this function is piecewise continuous, it has multiple values at the same point. So it has this value and has this value. So that is multiple valued. So it's not single valued. So then finite, this also y over x is also infinite at x is equal to 0. So that cannot be a valid wave function. So these conditions, we can say there are 4. We're trying to see what the valid function, valid wave functions. So those are the valid wave functions. If you're from India, they are valid or something. But so now we have seen that. So maybe we can. This integral is taken over all space. That means from negative infinity to infinity. But we put v because v encompasses negative x to positive. I mean negative infinity to positive infinity for x. Negative infinity to positive infinity, infinity to positive infinity for z. And so that is what we mean by for all space. So if you integrate it throughout that volume, the integral should be finite. And if of course we know that for certain the particle is within that volume now, that means we have localized the particle, and so the probability of finding that particle is actually 1. And so we can equate that integral to 1. But of course, you may not be able to equate the x coordinate to 1 or the y coordinate to 1 independently, but over the 3 coordinates, yes. But of course, if the wave is traveling with respect to time, much as they could be a wave function, in the time domain, you might have the particle not existing within that space, but that would be a bit complicated. This is what that if, for example, you're taking a volume here, and in that case, the equation will no longer be valid. So let's say that's our volume. So in case you have this wave like that, So if you integrate this volume here, and then your wave has left in terms of time. So well, it's a time varying wave. So that means that your integral, as you're saying, it's the complete volume. Your time coordinate is also important. So for most of these solutions, we assume that either it's time dependent or t is equal to 0 or t naught. So we take a snapshot in time. So that by default you should be aware of. The solutions with the time dependence can be a bit more complicated. Not impossible as you guys think, but they can be a bit more complicated. There are people who are doing probably bachelors in physics or something who will be, or that sort of physics. I've not yet seen a bachelor's in theoretical physics, but maybe it is there. And those will be the ones who might be interested. Or chemists also are interested in the solutions equation, because it sort of tells them where in the atom those electrons are going to be and so on. Anyway, back to what we're doing. We said that this, I don't know who can this bit, but I could be the guilty party. So the first order derivatives must also be continuous. That means dphi dx, dphi dy, dphi dz must be continuous. So why, you ask? Because where it's continuous. Let's have a look. Now, because you have a second derivative, there's also the value of the second derivative gives you what? Gives you either a maxima or a minima or something. It's just constant. So the reason a solution must exist in the derivative is because go into that detail. No? Okay. As you we'll sort of see what the gradients mean for this wave function, but anyway, dy dx must also be continuous. So once we solve this Schrodinger equation, the acceptable solutions contain the total energy, which is what is a bit cut off. Be able to spell it properly. Let me just do a paint window, which you may not or may be able to see. the screen, but I'm not seeing the. Oh, I need to scroll down. Zoom out and then just do it once. Tell to call them. And from here we move to here. It's solving the time-independent Schrodinger equation. Find acceptable solutions exist for only values of energy. So you remember that quantization, but in this case also not all energy values have, or actually in other terms, the solution of Schrodinger equation limits the value of energy. Yeah? Now, before we need to solve, so anyway, these are the three main conditions. One, the total integral is continuous. Maybe the integral should come in as number 3 because you need the functions to be continuous, finite, and single valued. Then this must also be continuous, not necessarily single valued, but continuous. Then in solving, one of the reasons they have to be continuous is that you need to be able to get the wave function. And if they're not continuous, that means you cannot differentiate over that segment. So you can't get anything out. You can't get it. For assumptions before deriving any sort of wave equation in the quantum mechanical field. Now, what that with the de Broglie and Einstein postulates. So, fair enough. Number 2, where's the okay, number 2, it must be consistent with the equation which we're going to paste on. E squared is equal to p squared over 2. Let's just paste this here shortly. Let's see. Oh, you guys are not seeing this, but since you're seeing it anyway, I wanted to take it to the other side. You pasted in the wrong window. Let's look at the text. So let's adjust that. So now that it's adjusted, we can go back to zooming in a bit. So we said that in order for us to derive or even solve we must be consistent with the de Broglie and sorry, I did finish the intro. In order to be able to derive and in fact solve these conditions must be true. Of course, we can't solve an equation for which during the derivation we broke the law, and vice versa. If we're breaking the law as we're solving, then we'll not get a proper wave function. Okay, then it must be consistent with the conservation of energy, which I've already talked about. E is equal to K plus PE. P squared over 2m plus V must be in XT, such that if you have two solutions, phi 1 and phi 2, you add the two solutions, they are also a solution. So that's what linearity means. So that is what you see there. Epsilon is sum of all functions. So you remember when we're adding up these waves here. So even for, but that's also allowed if we're drawing them coaxially. But we're having all these waves, and then you remember we added them to get a wave packet. Well, what made of it? So add this. Some people addition arithmetic also use the wave packet. They're not sure of the answer, but they know it is in there some. That's a joke, I think. We'll see some laughing emojis later on. So yeah, so the wave function, the individual functions and the sum of the wave functions is also a solution. Now, the constants must be such that the wave functions are continuous. What are we talking about? We're saying that, okay, I'm calling them constants, but that is a misnomer. This coefficient, I think here is a bit hard to see. So these coefficients here, C1 and C2, they must also be, sorry to call them constants. Those coefficients could also have values. Like, you remember when you're doing they could also have functions of X or functions of Y or functions of T in this case. So, but we're imagining that these might be in the wrong paint. This is the right one. So we're saying that C1 and C2 should not be functions of X. Means the combination of these solutions gives you is also a wave function. Now, okay, we are going to share from the PDF again because that doesn't need a lot of explaining. What that means that since those solutions, I think I've hinted about it. Since the sum of the solutions is also a solution, it helps us. I need to first close this PDF. Okay, it has one. Oh, I need to first print screen. still trying to just get this text. Because if I close now the PDF reader, will close. And it has been. Note that the above solution is arbitrary, this linearity. Yeah, we already have the texts here. Let me just present that again. Okay, it's back. For some reason, it has decided to be kind. Okay. This linearity requirement requires that the wave function can be added together to produce constructive and destructive interferences. So you have a particle and then wave, and then wave, and then you have a particle. So you have the three scenarios. You have particle, and then the wave has been generated from the particle, and this which, let's imagine, it has generated a particle, and then you have the particle and the wave existing at the same time. And so this is more accurate with this picture here is the most accurate in terms of what the wave function and the particle is. So the wave function, that wave, the resultant wave or solutions of that wave govern the motion of the particle. Wave function governs so it governs the particle behavior. The particle. So it governs the particle. I can call it motion or behavior. So we're here. So this picture 3 is the most correct. You can blue tick it. You can double tick it, not blue tick it. You can blue tick the other ones because they're not correct. So let me see if there's any feedback for now. Samantha Kesha is asking for help. We have Ronald couldn't see the screenshot. I hope you're able to see it now. The screenshot, we are using Paint and PDF, so I don't. Alan is also having some problems understanding. I don't know what the issue is. Kesha is back, the one who was asking for help. Alan, I think you have to go back and rewatch this. I also provide some other resources for you to be able to follow along. But that's a good thing with the recording. You can always go back and listen in, and sometimes it's to help you understand what you've missed. But in a no? Now, so this wave function allows you to have this destructive interference, so that you're adding particles particle 1 plus particle 2, or subtracting particles, particle 1 minus particle 2, maybe a small piece remains. That whole construct is actually, it would all be weird, right? Yes, let's just need just 1 minute.
Try to zoom out.
We are back. I needed to get some water. I'll try and make sure that you can't hear the drinking part. Before I went off, I think someone was asking to zoom out, zoom in, zoom out.
Try to zoom in the screenshot.
No, in the PDF anyway, so the only problem is zooming in. I lose some information which I want. But you can zoom into your own screen. If you're using a laptop, it's a bit harder to do. But for the phone, you can zoom in like it is on your screen. Zoom in. Okay. Also, for your phone, you can change the orientation so that it automatically goes to landscape. You have a better experience with this. Yeah. Of course, mine is not a landscape because the other things I need to see. Yeah, change the phone orientation or something, and then you can pinch, zoom to pinch. Sorry, pinch to zoom. Okay. So So we have seen that this wave function governs the particle motion. So I don't know, this might be, once you see how this come about, we're saying that the wave function and the particle are coincident. Phi plus particle. And this is really Max Born's work. Coincident. We're not looking at like a transmitted wave or anything. So they're not like independent. So in the Schrödinger equation, this V is the same as all the forces that acting on the particle show up as potentials, because these particles so all forces on them show up as potentials. So you can integrate F is equal to we say that if you move a particle of charge potential V, this is the resultant energy. And then that means that what does this mean? So this force is a bit like the electric field. Is it? V is equal to I think this bit is almost a bit like potential. I think a bit, no, it's not the same. But if you integrate the work, the force times dx, you get the work done. And if you multiply this by the charge, you'll end up with energy. So the work done by the force times the distance gives you the potential. Once you multiply this by the charge, you get the energy here. Charge, you can just put a Q. So this is for energy, not for field. So the force is like the second derivative of the potential. I mean, the acceleration is like the second derivative of the potential. But in this case, the acceleration is not what's important. From F is equal to ma. So I was trying to relate it to this acceleration because A is you differentiate this, you differentiate velocity one. So we have already looked at this even before we talked about Schrodinger. It was interpreted by Max Born, and we began to apply to collisions of particles or to interaction of particles. So you can't measure this quantity psi directly, but you can see that there's if you get the, what's that thing called? The conjugate times the function, a plus jx jb. So the complex conjugate is a minus jb. And then, so if this is equal to z, then this is equal to z with that style. So if you multiply this, you end up with the positive value. Which would be equal to the magnitude of z squared. So anyway, for a long time you'll see that and then times dv. So sometimes you just say that the square of the magnitude, but really the square times the volume of the total distance coordinate gives us what? Ability density of finding the particle. Okay, you're right. The square gives the probability density. So if we sum up probability density, so sometimes probability density is given by probability, it's by function, so it becomes a probability density function. So if we sum up that for, I don't want to use V a lot because people will get confused with potential. So if we sum up the PDF of, we get the total probability. And usually it's if so, you can't just sum this. So it will be that the V and the X or the V. Well, okay, it is a bit clear there. So with those few lines, we conclude this this section here. So I think the symbol in this font is not there, but that should be a psi. Psi times psi over the volume should give it. So this is what we call normalization of the wave function. So if you normalize everything, that means you're measuring it on the, remember the normal function, normal distribution, all values on the normal distribution are between 0 and 1. So normalizing means putting it on a certain scale. So if you have, let's say heights 1.5 meters, 0.2, 1.8. So you can normalize these heights to 1, such that everyone is a fraction of this one height. So that would be 0 point something. But also 0. Okay. Write fast this thing. 0 point another thing. You can't write fast like in Paint. So this is what we call normalization. Now we have finished that bit, so we're going to some of the solutions. Maybe These solutions also take a bit of time. I even hope we can look at one maybe. So we're going to look at eigenfunctions and eigenvalues. You guys did a bit of matrices, so you might know what these are. The pencil. So eigenfunctions are if you have an equation let's say dy dx is equal to 3. This equation. So the solution also will give some conditions, maybe when x is 2, y is 5. We can give other conditions that when x is equal to 2, y is equal to 5. If we give conditions for when x and y are 0, whatever, or dy dx is equal to 0, those are called initial conditions. I mean boundary conditions. So conditions on time are called initial conditions, but sometimes we use initial conditions and boundary conditions interchangeably. But that should be it. So these are we can call this your initial conditions. Now we'll solve this and we'll end up integrating 3 with respect to x, and then we'll end up with x. And then some people will be smiling, but there's a constant. Yeah, there's always a constant. Means to remind you when you've forgotten the constant. So now this is what is called an eigenfunction. So we have actually solved this equation, but we ended up with the function. And so we need to get the eigenvalues. So we substitute for 5. 5 is equal to 3 times 2 is 6 plus c. Okay, I told you this thing is built for speed. It's 2. Which gives us c as negative 1. Now, after we solve this, then we'll get maybe y1. Right? So y1, I mean x1, sorry, x1 will give us a particular solution for y1. But it is frustrating to be slow. So x1 will pass a value of y1, and this value of y1 is what we call the eigen. Let's use this. It's what we call the eigenvalue. So that value of y1 is what we call the eigenvalue. So in this case, we have solved this. So you have your solution being made up of x 1 between x infinity, which will give you y infinity. So all these, when you add up these eigenvalues, they give you your eigenfunction. So if you added up x1 to x infinity, they give you eigenfunction. But in this case, these solutions here are different for the Schrödinger equation, and we're going to see that. But understand these concepts either in this way or in another way is quite important. So now, a lot of times we're going to look at a function which is an operator. I already used it for this del operator, either in this, that's probably last semester or this semester, or sometimes which is that del operator. So this del is almost the same as the d. So actually, for most of the solutions of the Schrödinger equation, you have that del operator. We don't have a d. Some of you guys call it a partial derivative, but in other cases, there is a slight difference. So you can also have a constant and a function. So there's that constant is operating on that function. From the function, you get the eigenvalues. Or eigenfunction, sorry. Okay, there are a number of steps to guide us. It's not that you must completely follow. So what was in the notes at first is something else in terms of deriving. Maybe we should put derivations in quotes. You remember what we had this bit here? Well, this has just been converted to x and time coordinate, but we had this equation, but we're using it differently, right? So in this case, you can have a del operator, which is like d phi 1. So you have a second operator, which is let's phi dt. So that differentiation or partial differentiation can be seen as an operator, and then you get your solution of. So this is what you have, that momentum. This is the momentum operator, and then this is the energy operator. But these come from, you can have a look at this and see how they are derived. From the last lecture, I should have a pretty good idea. So if I have it is I times h. So remember we said that you can have a constant then operating on a function, but in this case you have also this x. So it can operate on something. So that function can operate on something. Good. And once it operates on something, these operators, we can feed them the time function and then the x function, and then they'll give us the derivation of the Schrödinger equation. Remember, this is equal to p squared. There used to be some way called p squared. over 2n. If you're having problems with the audio, you can turn on the captions. The last time they were not good, but they're better than having no audio experience. So the captions, of course, are texts. Maybe, I hope Google picked up the complaint that some of the words were not being translated into proper words, or actually appropriate words. Indeed. Let me see, is there any charts that we're missing? Yeah, you need to pin the screen, otherwise it keeps disappearing. You get the most active participant at that time. Now, we're saying that these are applications of Schrodinger equation, and we're saying that we'll see how Schrodinger's equation is solved and how the particle is subjected to various. You guys need to read this because I've already read it. Yeah. Okay, subjected to various conditions. Then that is why we need this bit, the solutions, to see how Schrodinger equation is solved. The particle is subjected to various conditions. Then we need to learn the characteristic properties of solutions of this equation, and we need to compare predictions of quantum mechanics to wave mechanics to those of Newtonian mechanics. So we're going to look at limitation of energy to specific functions, really seen, but once we are doing either particle in a box or something, we're going to see the restrictions that come up to energy. I call them additional energy restrictions that are brought about by Schrodinger's equation. So we're going to our very first solution. Would you? That's exciting. And we have how many minutes of charge? 50 minutes. Okay. So I want to first look at free particle, but before we look at the free particle, we need to look at general solutions of differential equations. So if you have a lifting, I don't know, maybe they are out of data. Yeah. By the way, I know most of, I don't know if you have good like a mobile coverage. Recently I was traveling and I found that for the roadside, at least they have decent coverage. For interestingly big parts of the country, sometimes it's better than the traditional networks. Of course, the data costs, they are much cheaper, but this is not an investment in case you have control experience or whatever, or you have your preferred provider. So choose the one solutions. So again, it's also important to know what solutions you have. Now, all solutions to this differential equation defy dx squared plus a constant of phi d. Let me just take a screenshot. The quality is usually not as good as No. All I did was take a screenshot. How is it that I take a screenshot and it's not a screenshot? It was over zoomed in. Désolé. Of course, for those who know some French, désolé. Désolé. Oh, sorry. You zoom in, zoom out. Characteristic. Will not be intimidated by these things. Let me just change what I'm sharing. Just make sure, in case you've been pinning, you repin back what I'm sharing. Chrome tab, a window, sorry. Let's first go to the other one instead. Yes. Yes. Okay, I'm presenting to everyone. I know that. So you have a d2y. Sorry about the voice. d2y dx squared is equal to ky. No, it's not equal to another. Désolé. Root is equal to 0. So this equation has, well, it has only 3 solutions. Number one is when k is positive. And k positive, of course, you can take it to the other side, and then you see that it will be ky squared plus ky. Do you guys want to see it? I don't think so. Dx squared is equal to ky. So for when you first integrate, okay, is equal to negative y. So it will become dy dx. The reason it has a few of these solutions, sometimes, let's just imagine we're using operators. Y dx is going to be equal to negative ky squared plus a constant, which we'll call C1, which you can call A. Not many subscripts. A is a bit weird. Okay, let's use B. And then Y is going to be equal to K over 2 Y cubed so it is really weird. No, it's like a bit weird. The solution to the third power is going to be weird. So that's a negative. You can use a del operator to be able to bring it out closely because it squares the function instead of just having this derivative thing. So if you're using del y or del squared del x squared. So if you're using this, it brings it out easier. So you know that when you do the inverse, you'll end up with y squared minus ky, okay, plus y is equal to 0. So you can get solutions of this. This is going to be y into y plus k is equal to 0. Of course, there's a constant. So the solutions are going to be y is equal to 0 and y is equal to negative k. Does that make sense? No, it doesn't make sense. Why doesn't it make sense? Okay, y is going to be equal to a constant, but why should it make sense? I don't know. But it's not really a constant because okay, so when we go back to find this that derivative there is that yes. Remember how do you end up with this 2me? P squared. It was p squared over 2m, right? You need some background knowledge to operators too. I don't have to go there for me to use the explanation, but let's just use convenience. So, and it's very much. So when we're looking at a free particle, we hadn't said here. So that means Vx is equal to 0. It's just slightly out. So once Vx controls the CPU. We'll be back. Okay, we are back. We should be ending soon. Okay, so we know intuitively that when we are differentiating our wave function, psi is equal to AE into J kx minus omega t mujukira. So when you had this, so if we differentiate it twice and get this, if you differentiate it twice and end up with a negative J, I mean J squared, it will yield a what? A negative something. So I would that where. Let me just quickly present this window and then go to another one. Was it? That once it's equal to 0, that one you can solve. The x. This one you can solve very easily. So you get a constant plus, which is what we had done at first. But this other one needs this. That if it is positive, then you can't have a kj here because after I square it will be negative. If it's negative, intuitively you should know there was some sort of imaginary component. So that's how you end up with these 3 solutions. So solutions, or there's actually a way of you to solve that equation and get those solutions using your math. Till now, let me stop presenting this. I want us to be done in like 5 minutes because my time I'd planned for the meeting is nearly up. So 21. All these this is a free particle. So what does this mean? That our potential is 0. So our solutions here for a positive k. So that means your wave function is given by the most free waveform, which is the sine and cosine. So this could also be represented as A, E, no, I don't want me to write this slow, but challenge accepted. So in case you're there, this has me to write really slow for characters to come out. So just you have that true function that, so for a free particle, this is the solution that we're interested in. Let me try and see if this will stabilize. So that's what we have there. I don't know why this thing is acting up. Let me just share one more time. My diagnostics so that I see what is happening. I hope, and since people are already on, that means the one. Okay, it has joined with audio, so sometimes it joins without audio. That screen. So for a free particle, definitely the solution is going to be what? A waveform, sinusoid waveform. It's not that sinusoidal, but I don't have time to wait for the cursor to mark properly. And then you can for a free particle, right? Fx plus g, that means it's a constant. Now, what happens? We know that for this function, as x tends to infinity, it is not going to be finite. And network is acting up 5 minutes ago, but network just keeps going off. So the good thing I've someone sharing from, so I can tell I've gone off. Epsi, your eigenvalue is going to be equal to G. So it's going to be the screen sharing. I started sharing a bit longer, like 30 seconds ago. So If function is going to be equal to G. So if in again, I unmuted, but let's recap briefly what I just said. We said that if your energy is equal to 0, you're just going to have this constant line. And then we said that for as far as x is constant, this is going to be a constant. But if you had a time dimension somewhere here, then so if it is a constant, it's not what you call waving. There's not much of a wave if it's a constant line. But in t, other things could be happening in the t plane. What is like constant function. So something else could be happening in t, but if nothing is happening in the t domain, then it's also okay. Then with that, the two solutions are for n is for n energy is equal to 0. Unfortunately, the cursor is not moving, but that top line is equal to 0. And then those dots represent when E is non-zero. Just have that sinusoid. And then we said that tomorrow, sorry, which I've made the same mistake again as when I muted. On Wednesday or next time, we'll look at this bit here. When you have a certain potential, sometimes free, and then you have a potential on this other side as well. So you have V1 and V2, and you move from somewhere where the electron has been moving relatively freely to some other potential. So, and this potential is higher than the energy of the electron. So we're going to be seeing that tomorrow, and that's from dy. dy dx. I think it's annoying to write. But they gave that equation for that, and then I disappear from this broadcast. The actual eigenvalues to get the actual final solution, but there are only 3 solutions, maybe not just 3, but 3 of interest, and they're dependent on that value of k squared. So I lost my main audio, but I've just reconnected this here. So otherwise, have a good day. I don't know if there are questions in the chat that I need to look at, but let me